Hello friends. Today we've got a quickie, a calculus trick that we need to solve a little first order ordinary differential equation, as we can see in front of us. Calculus trick is really nice, really smooth. We're gonna go and we're gonna multiply this whole function, the whole equation, by an arbitrary function mu of x. You know we like our arbitrary functions here, right? So we're gonna have mu psi prime plus mu p psi equals mu q. So far, why the hell did we do this? Well, since mu is arbitrary, why wouldn't we say let mu p be mu prime? P is a function that we have, function of x, but mu is completely arbitrary, so we can definitely find such a function. In fact, such a function is mu prime over mu equals p, or if we integrate both sides, we get ln mu of x equals integral of p of x dx. Simple. Or I could exponentiate both sides and get mu is equal to the integral e to the integral of p dx. There we go. So that's what we multiplied by. And if that holds, then what we have is mu psi prime plus mu prime psi equals mu q. But mu psi prime plus mu prime psi is just mu psi all prime, right? It's a product rule, Leibniz rule, whatever you want to call it, is equal to mu q. Now, all we need to do to get mu psi is to integrate both sides. So we integrate with respect to x. There we go. And now I am just going to add the constant c. The formula gets a little bit obscure if you don't put any constants anywhere. The reason why I didn't add any constants here is because mu is arbitrary, right? So I can multiply by c e to the p dx, but I can also multiply with just e to the p dx. But this one isn't arbitrary. Of course, if you have an n-order differential equation, you're going to need n constants if it's not a determined system. I mean, if you don't have boundaries, right? So this is our constant. It's the only way to get one. So if we have that, and we know mu, now all that's left is to express psi of x by dividing by mu, and we get that psi of x is equal to e to the minus p dx, which multiplies c plus the integral of q e to the integral of p dx dx. Now, if you were to solve all of this, you would want to change the bounds to some other variable just so you don't get confused. So here you would, for example, integrate from over x1 to x2, and then this would be x2, and then you would get x, right? But we're gonna see a very simple example now. Breathless. I really like this trick, I guess. Or maybe I'm missing my tea. Anyways, the differential equation that we had last time was psi double prime minus k squared psi equals 0, and then we dismantled it into d squared minus k squared psi, and we saw that a solution of d minus k psi, when we dismantled it, was psi of x equals e to the kx constant. Sure. Let's use c e to the kx, right? We saw that was fine. So if we know that, let's see if it works with our formula. With our formula, q is equal to 0 and p of x is equal to k, which is a constant. So p of x is constant. And we just plug that in. We plug that into 1. And we're gonna get psi of x is e to the minus integral of k dx times a constant c plus q is just 0, so 0, and that's equal to c e to the minus kx. We have minus k, so p is minus k. My bad there. Everything works out. There we go. C is e to the kx. A bit dirty, but what you gonna do? Those pesky minus signs. Anyways, that's the calculus trick that we're gonna need. This one. So commit that to memory, or better yet, watch the video again so I get more views. So we're gonna be using that next time. Bye.